So the next topic that we have today is simple harmonic motion, and the word simple kind of leads you to believe that it is somewhat simple. And I don't think it should be that hard, but I do know that anytime you add words to a question, most math students find that to be immediately like off-putting and a little bit scary. So we're going to be starting to deal with this idea of simple harmonic motion. And with simple harmonic motion, we're just going to take it from beginning. And you actually have this in there in your Google Classroom. I actually shared this PowerPoint with you if you want to have it that way. But honestly, following along with your notes is probably a safer bet, and you can look back if you want to at a later date. But this is kind of the idea of simple harmonic motion, and I hope this comes across correctly in here and that you get to see that. But in simple harmonic motion, we're basically going to be taking a look at physical phenomenon and trying to kind of represent that as trig, okay? So keep in mind, math was not created for math classes. It was actually created to actually figure out what was going on in kind of real life scenarios. So each one of these things that's popped up here on the screen are examples of things that actually display simple harmonic motion. Now, one thing that's kind of a strange idea, when you think about a pendulum, you probably don't think about this as a trig wave, do you? Does that look like a trig wave? And I will admit that the first time I tried to start explaining this to people, I kind of messed it up myself. I had this really cool experiment that I was going to show, but really what we're doing is we're going to model it's not the position X versus Y, it's actually where it is versus time. So time becomes sort of the big thing. And so what's kind of cool is a pendulum, that's a grandfather clock, right? It just goes back and forth. And what's really, really cool is that pendulum, you'll see that over time, and I hope we have enough time to discuss that. Have you guys ever been to the playground where you're kicking your feet as hard as you can to get as high up on that swing as you can? Is that a pendulum, by the way? Are you going back and forth? So if you kick your feet as hard as you can to get flying, if your friend was watching on a stopwatch from peak to peak, that would be a period, right? That's a full cycle of your story. And let's say it took you, I don't know, what would be a reasonable amount of time? I mean, maybe like 4 seconds or something like that grand total. What's really bizarre to me, it didn't make sense when I was a kid and I saw it, that the physics makes this happen. But then you've also probably had another experience when you're just chilling on the playground, talking to one of your buddies, and you're just sitting there kind of gradually swaying back and forth as you're just kind of talking to each other. You ever done that too? Do you know that if this radical one where you're trying to do, and you're going to see if I can do a backflip and break my neck or whatever, if that was 4 seconds, then you know when you're sitting down and chilling with your friend talking, that's also 4 seconds. And it doesn't matter if I'm sitting on it or Brianna's sitting on it. I picked you because you weigh a bit less than I do. Because I weigh a lot now. Dang it. Anyway, I'm trying, but failing. Anyway, it doesn't matter the weight. It doesn't matter how fast you're kicking. You know, the only thing that actually matters in the story of the pendulum is how long the string is. How long are the chains that you're sitting in? Which is why with a pendulum, an important little feature is on a grandfather clock, there's always a screw down at the bottom. There's this line that comes down of metal, and then there's the bell at the bottom, and you'll notice that there's a screw on the bottom. And that screw, if you unscrew it, it makes the bell fall a little bit. It makes the length longer. So if you need it to take longer, you just lengthen it a little bit, and then it'll adjust the clock to make it more accurate, or if you want to screw it back in. But that's also why it's a little bit dangerous to move those. If they get out of adjustment, then they will always then be out of adjustment because it will be telling time wrong. But as it turns out, the swing of a pendulum is going to be modeled as either a sine or a cosine wave. This thing right here, what am I trying to show you? What is that? I'm pointing to this guy right here. Ooh, I guess this guy. Be like a radio tower. Well, you know, when you go to your radio, it's a little bit interesting. As I mentioned last week, at least I should have mentioned last week, and I think I missed it with you guys. We've talked about period before, right? So it turns out if you know that the period of a wave is something, then its frequency is just the reciprocal of that. So if your period is 4 pi, then your frequency is 1 over 4 pi. And that word frequency is kind of significant because when you go to your radio and you turn your dial, your FM, you know what you're actually doing? You're doing frequency modulation. You are turning your radio to a certain frequency. So when you put it at 100.7, that's the one I like. Classic rock. You know, I mean, I actually don't listen to classic rock in my classroom. I actually like more alternative stuff. But in my car, I usually do that one because that's the one I have. But that 100.7 means 100.7 thousand waves per second. That's the frequency. Every second they're doing that. And so when you are turning your radio, you're telling it to read that. That's what FM radio is. It's frequency modulation radio. Whereas AM is, any guesses? What A word have we used in trig? It's amplitude. It's the amplitude modulation. So you're actually saying, okay, radio, please hone in on waves that are this high. And so when you amplitude modulate, you're actually saying, I'm only going to look for waves that are this big versus the next thing. If I turn the dial, now I'm looking for waves that are this big. And turns out you'll notice that what's on AM radio is talk, right? And you'll notice when you go up into the mountains, you can keep getting the AM radio stations, which all the kids are like, boo, and the adults are like, sweet. You know, it's just kind of funny how that works. Like on a trip, talk radio makes things go much faster than music does, but music is more like just naturally enjoyable. But, you know, on a trip, sometimes like listening to talk is time consuming, and that's what you want to do is just make time fast. But amplitude, it somehow the waves are bigger, and so it's able to go around things. So when there's a mountain or something, some of those waves are able to kind of, because they're curving this way, they can get over things, whereas the FM doesn't. So AM goes longer distances and gets around things better, but FM has more clarity, doesn't it? You get to hear a little bit better. I think this one right here is fairly obvious. Bottom right, I can't seem to make my cursor get there, but bottom right, what am I trying to show you? Ocean waves. Now, as it crashes, you're losing some of that periodicity because it kind of stops. But if you go out and you look at those swells, do those look like the sine and cosine waves we've been studying? And then the other one is the spring mass, and that's weird. But if you take a spring mass and you hang it from a ceiling and you just pull it down and let it go, you're not going to talk about the X versus Y, but you're talking about its height versus time. So if you could actually take, and in fact, we could have it. It's pretty cool, and I don't know if you know that, but they have some radar detectors that you can actually, some motion detectors that you can actually hook up to these things. There's these TI lab things, and they're really, really cool, but also they're very expensive, and so no teacher ever has them, at least not this teacher. But I've never had one, but I've seen them before. But literally, if I hook this up and I put a radar detector, this motion sensor thing under, and I pulled it down, and I told it to map the height of the object right above it versus time, you're going to get a beautiful sine or cosine wave. So keep in mind, if I pulled the mass up to the highest, what did I do to the distances? I made it a maximum, and then I dropped it and it goes like this, right? What would that be? What would that model if it started at its maximum? What is that? Starts at the maximum. That's a cosine wave. Doesn't a cosine wave start at the top, come back to the top? What about if instead if I pulled the mass down and then let it go? So that'd be a negative cosine, isn't it? Generally, when I look at these things, I have a choice between sine and cosine. You know which one I go with? I would go with cosine because a cosine is easier to see the top or the bottom. A sine wave goes from the middle. That's a little harder, but I can do that with a weight if I set the thing under it and I just took a stick and I just tapped it. As soon as I tap it, it was already at rest and I kicked it up, right? So it started doing this. Now, again, this is called simple harmonic motion, and the reason it's called that is, you know what I'm going to ignore for the moment? Friction. Because what really happens as soon as I kick that thing and make it start wobbling? Well, gravity's in there and that's going to make it keep doing that, but will it keep having that same amplitude up and down forevermore? What really happens? Well, air friction is going to be part of it, but won't it lose its energy just a little bit? Now, energy can't really be lost. It's just transferred and moved around. Well, there's little molecules in the spring, aren't they? And those molecules actually are going to be bouncing into each other as you make it do that, which is going to transfer this tiny little bit of heat into there in the form of friction, and you're going to lose it by the transference. And that's called dampened harmonic motion because it's actually going to become a little bit less over time. Is that real? Oh yeah, of course it is. We're going to ignore that for right now, okay? Because that's really complicated. We're just going to look at the easy stuff. So anyway, that was a long introduction, but here's the deal. Now, physics does this a little bit different than math does, and we're kind of delving into physics land right now. So just be aware of that. An object that moves according to that information is called simple harmonic motion, and here's where it goes. So there's a lot of information here. I wish I had done this in a slightly different order, but I didn't. Let's see if I can make all this stuff pop out there like it didn't go. So for some reason, my equation did not pop out of there. So it should be A cosine omega t. A cosine omega t, where omega is this, that little W looking thing. Now notice that they use omega. See how it says the period is 2 pi over omega, that W looking thing? So you're going to write in those two little gaps, A cosine omega t. Now, one thing that's a little bit interesting in a physics sense is there's some of the things that we're not going to put in there very frequently. One of those things that we don't usually put in there is a vertical shift. It commonly doesn't exist, and there's a reason for that. If I can go back to the weight idea hanging from a spring, which I think you guys can relate to, picture that. If the weight is hanging there from the roof, would it make sense to say the resting position of that weight is 0? Can I just call that 0? I mean, you're right. I could say, oh, well, it's 4 feet off the ground. I'll start to call it 4. Could I do that? Yes. But in a physics problem, where is 0? Wherever I wanted it to be. And I probably wouldn't walk over and say, after 6 seconds, I clicked it, right? I hit the button. I'd say, no, at 0, I hit the thing, started it going. So you can make time and height wherever you want because I have control over it. It's my experiment, right? So it makes sense. So that's why I said it was A cosine omega t. We don't have a phase shift. We don't have a vertical shift because in a physics experiment, I get to make the rules myself. So they use omega. We use B. What are B and omega? The same thing. Math uses B, physics uses omega, and believe it or not, music, dang it, they use the letter K. But B, omega, and K are the same dang thing. Exactly the same. Let's move on. Okay, so an object at rest is coiled spring, pushed up a distance of 4 feet from its rest position, assuming it is simple harmonic motion with a period of 2 seconds. Let's write an equation that relates the displacement of the spring from rest. Well, okay, so let's think about it. What pieces of data do you have? Well, it's either going to be a sine or cosine, but it says that we actually took the object and we pushed it up a distance of 4 from that rest and then released it. Would that be a sine wave or a cosine wave if I brought it up to its maximum and I let it go? That's going to be our cosine wave. That's our choice. Now, what other thing do we have? See, that's the formula physics uses. What does A right now? Do you guys know? It was 4. Why? Because I moved it up. I stored potential energy in this form of moving it up that 4 units. Now, the other thing that you did right there is we know that the wave happens how frequently? 2 seconds. So hopefully this all shows up the way I wanted it to be. Oh, it didn't. Okay. Why is it pi? Because what's the formula we used in math to find the period, everybody? 2 pi over b. 2 pi over w is the period. But if 2 pi over w is 2, then what does w have to be? Is it has to be pi. It's a simple little story. It's pretty simple. I think this kind of, no, it didn't. Anyway, it should be 4 cosine pi t, and a couple of those things got orphaned when I changed something into Google Slides, I believe. But this t right here is supposed to say, it won't let me come over, so it's supposed to be 2 seconds, and it showed that cross multiplication. So anyway, I wish this worked a little bit better, but it didn't. So when we go through all of this, what does the negative mean? It just got tapped down, something like that. Fairly simple little idea. Notice there's no phase shift. What would the period of this particular one be? Be careful about this. The period would be 2 pi over. How do you find the period? 2 pi over b or omega or k. So it'd be 2 pi over 4, which makes its frequency 4 over 2 pi. And its frequency is how many waves per second you would see or per minute that you would see. So this is kind of how the thing would look. Hopefully this is all going to look right. Please show me what I wanted. And so what that means is, dang, this is really frustrating. The frequency is how much is going to be completed in that 1 second. So if you look at this one, 2 pi over 4, let's take a calculator out. 4 divided by 2 pi means that in 1 second, I should see, so 2 pi over 4, let me double check that. 2 pi over 4 is the period. And then if I take the reciprocal of that, I get 0.63, okay? How much of a wave am I seeing in that 1 second? This is kind of weird. My period was 2 pi over 4. If I flip that over, my calculator says 0.64, okay? How much of a wave do you see right now from 0 to 1? 64% of that wave. That's its frequency. Okay? You kind of follow that? That's kind of a weird way of looking at it. We'll go a little bit further. So now this is actually the one that I wanted to get to because this is actually kind of cool. So have you guys ever heard of the London Eye? It's been in a million TV shows, you know, like if you guys, any of you ever watched Sherlock, the British version of Sherlock Holmes? It's really, really tight. But in the opening credits, they have the scene of the London Eye. And the London Eye is this massive, massive Ferris wheel. It's huge. And it really dominates the London skyline. So why would a tourist get into the London Eye? You can see everything. When you get on, you're down near the ground and you start moving on up. And by the time you reach the top, you get to see the whole skyline. So you're going to see Parliament, you're going to see Big Ben, you'll see the Thames, you'll see all of that kind of stuff. I'd love to do that someday, but I'm a teacher, so I don't have that kind of money. So this is the London Eye. And by the way, I actually modeled this. This is real stuff. I actually looked all this stuff up. This is a real life story. This is application of simple harmonic motion. So it says the diameter of the London Eye is 120 meters. Now, that's big, isn't it? 120 meters. That means if you laid it down on our football field, it would actually go from goal line to goal line and then some. It would stretch the whole thing. So when you put it up there, it's pretty high, right? And so when the rider does a full circle, they're 135 meters above the ground. So what does that actually tell you? There's something significant there. What's that? It's on a stand, yeah. So, you know, they want to make sure you get as high up as you possibly can go, right? So you're already 15 off of the ground, 15 meters, which is like 50 feet. You're already 50 feet off the ground when you get in the thing, which is pretty high. And then you're an extra 120 meters off the ground when you do that. You're pretty high up there. So if you're afraid of heights, the London Eye might be rough. And it says it takes a revolution every 30 minutes, which is a little crazy. So what does that revolution every 30 minutes means is that's the period, right? It's going to do this every 30 minutes. And so what we're going to try to do is we're going to try to see if we can actually model that as simple harmonic motion and come up with the equation that models that thing. So I think we'll keep going just a little bit further. What is its amplitude? Now, again, the diameter of the wheel is 120. Where's the middle of this wave? It's actually going to be the axle. You're going to go from below it to above it, aren't you? You're going to be doing this. So if the thing is 120 meters, then its amplitude is going to be 60. It's going to be the radius of that thing. So that's the first thing. Next thing is, if we sketch the path, what's going to happen? So I'm going to go ahead and stop hopefully this will allow me to. I'm going to stop this and reshare this with my document camera because I think I can just do a better job. So it looks to me like I got in 15 meters off the ground. It's got a peak of 135. And I believe if I got on at the bottom, it would do something like this. So what am I trying to show you that the path of the London Eye is? It's a cosine wave, but not a cosine wave even exactly, but a negative cosine wave. Does that make sense? It's a negative cosine wave. So let's keep going. We know that its amplitude is 60. You guys cool with that? And so that makes this right here 60 above the 15. Does that make sense? That's where the axle would be, 75. So I could put a 75 out here, can't I? Now, in this case, the rider kind of wants to know how high they are off the ground to see if they see something. So they're not going to make this 0 because that doesn't make sense. It makes sense to go, wow, I'm already 75 freaking meters up in the air. It's a long way. So anyway, it's way the heck up there. And if the period is 30 minutes, what was the formula that we did over that? 2 pi over omega is 30 minutes, right? So if we do this little thing that we talked about earlier called exchanging the extremes, then omega would be 2 pi over 30, also known as pi over 15 t. This is the height as a function of time. Well, one of the things that I kind of wanted to figure out, let's see what happens here, because this is actually worthwhile, because on the test coming up next week, you're going to need to know this. Can we find out how fast you're moving if you're on that thing? Let's figure it out. What is its RPMs? Well, I'm just going to go like here. I'm going to do 1 revolution per 30 minutes. Now, what was the value of a revolution? Well, a revolution is a full circumference, isn't it? So 1 revolution would be 2 pi r, isn't it? So if I did that, then I would have meters per minute. So 2 pi, that would be 120 pi divided by 30, is 12.566 meters per minute. Now, I don't know about you, but that doesn't really ring all that well. Is that a linear velocity, by the way? Meters per minute? It does make sense. It does work. But what's interesting is I actually took the time to do a lot more of the mathematics. What's a number that actually is a little easier for you guys to follow? Meters per minute, miles an hour, what rings better for you? I mean, do you guys know what meters per minute feels like? Yeah.
What is that?
12.5. There's a point there, sorry. 12.5. Can you guys picture how far 12.5 meters is? Football players do. Isn't a meter about a yard? So I'm thinking, in other words, on the London Eye, a distance maybe as wide as my classroom, it moves that far in 1 minute. Picture that. How fast is that? It's extraordinarily slow. It's about a half a mile an hour. It's very, very creepy slow. When you might go, well, why would they make it so dang slow? Well, because one, it's huge. But number two, when you are the one on it and you get near the top, where do you want to be? At the top for how long? A long time. And you're paying big money to get on that thing because it's a tourist attraction. So I'm sure it's pretty expensive. And you want to be up there as long as you can, right? Now, when you're in the fair, what happens when you get on Ferris wheels? They stop it and they let you off, and then they let so people are up there swinging around, and it's all cool. But they don't do that actually with London Eye. It never stops. It just moves and moves and moves and moves. And so when it gets down to the bottom, the doors automatically open and people walk off. It never stops. Why? Because it's only going a half a mile an hour. It's going so slow, it's very easy to step off the thing without it stopping. You can push somebody on with a wheelchair. It's no problem. You just push them on. It's fine. It's super easy, but it goes really, really slow. Gives everybody a nice 30-minute long ride, and it's creepy slow. But it's awesome if you're the one that's up there getting to see it, right? So, that's just what happens. So they never have to stop it. And that's kind of a neat idea. So what you guys are going to do is you're going to go to, in your Google Classroom, you're going to keep cruising through that assignment that I gave you. And that assignment is sitting in here. And I have it down as my, I guess I need to get over here to your class. Let's go a little bit further. Here we are. And here is your simple harmonic motion assignment that you're looking at. And so what's going to happen when you get into that, you can't see that. Sorry, everybody. Let's do that. And let's do a reshare with that. Here we go. Should be this guy right here. So now what's going to happen is you're going to try to model some of those. And so please understand that these are not supposed to be super long and difficult problems. The weight, it bounces a maximum of 8 inches above and below equilibrium. Well, if the whole thing is 8 above and 8 below, what did I just give you is the amplitude, right? It tells you that the time it takes to complete as a cycle is 2 seconds. What did I just hand you? I handed you the period. You can just kind of go your way through that whole story, and it shouldn't be particularly tough. But what I'd love to see you do is draw a picture, even when it doesn't tell you to draw a picture, because when will it be at its minimum height? As soon as you sketch one wave, you're going to see that because it's going to be at the bottom. When will it be at equilibrium or at the middle on the way up? You'll see that in your diagram. So question number 5 should be very, very easy. And so I'm going to go ahead and stop that video.